Today's lecture is on wave topics given in chapter number 10 of Physics for Class 12. The syllabus for the academic year 2021 has been revised. Some portions like resolving power of microscope and astronomical telescope, polarization, plane polarized light, Brewster's law, uses of plane polarized light and polarides has been deleted. In your board examination, there will be a total of 9 marks questions on this chapter, which is distributed as 5 marks for long answers, 2 marks for short answers, and 1 plus 1 for very short answers, or it can be 5 marks numerical problem plus 3 marks for short type answers type 2 as well as 1 mark for VS, very short answer. Please study it very carefully and make your own notes. This is very important but very short and very easy chapter to study. Please prepare well by making your own notes from this video presentations. 1 mark questions. Question number 1. Define wavefront. Answer. A locus of points which oscillate in phase is called a wavefront, or a surface of constant phase is called wavefront. Question number 2. What is the shape of wavefront obtained from a point source at a small distance, that is part 1, and part 2, large distance? Answer. For part 1, that is for a small distance, the wavefront is spherical, and when the distance is large, the shape is plane wavefront. Question number 3. Under what conditions a cylindrical wavefront is obtained? A cylindrical wavefront is obtained at a small distance from a linear source of light. Question number 4. What type of wavefront is obtained when a plane wave is reflected by a concave mirror? The shape obtained is spherical and converging. Question number 5. Who proposed the wave theory of light? Answer. Christian Huygens proposed the wave theory of light. Question number 6. Name the physicist who experimentally studied the interference of light for the first time. Answer. Thomas Young. Question number 7. What is interference of light? Answer. The modification in the distribution of light energy due to the superposition of two or more waves of light is called interference of light. I repeat this answer. The modification in the distribution of light energy due to superposition of two or more wavefronts of light is called interference of light. Question number 8. What is the maximum intensity of light in Young's double slit experiment if the intensity of light emerging from each slit is I0? Or what is the intensity of light due to constructive interference in Young's double slit experiment if the intensity of light emerging from each slit is I0? Answer. Maximum intensity of light in Young's double slit experiment is 4 times I0. Question number 9. Define fringe width. Answer. The distance between two consecutive bright that is, or two consecutive dark fringes is called the fringe width. So fringe width can be the distance between two consecutive bright or two consecutive dark fringes. Question number 10. Instead of using two slits as in Young's experiment, if two separate but identical sodium lamps are used, what is the result on the interference pattern? Answer. The interference pattern disappears if two separate identical sodium lamps are used. Question number 11. What is the effect of interference fringes when yellow light is replaced by blue light in the Young's double slit experiment? Answer. The fringe width decreases if yellow light is replaced by blue light, since beta is proportional to lambda and lambda is smaller for blue light than yellow light. Question number 12. How does the fringe width in the interference pattern vary with the wavelength of the incident light? The fringe width is directly proportional to the wavelength of incident light. Question number 13. What is the effect of interference fringes in a Young's double slit experiment when the monochromatic source is replaced by a source of white light? Answer. The central fringe is white. The fringe closest to on the either side of the central white fringe is red and the farthest will appear blue. Question number 14. How does the fringe width in interference vary with the intensity of incident light? Answer. The fringe width is not affected by intensity of incident light. Question number 15. Which color of light undergoes diffraction due to maximum extent? Answer. Red. Question number 16. How will the diffraction pattern due to single slit change when violet light replaces green light? Answer. The diffraction bands become narrower. Question number 17. Do all waves exhibit diffraction or only light waves? Answer. All waves exhibit the phenomenon of diffraction. Question number 18. We do not encounter diffraction effects of light in everyday observations. Why? Because the wavelength of light is much smaller than the dimensions of the most of the obstacles. Question number 19. Why are diffraction effects due to sound waves are more noticeable than those due to light waves? Answer. The wavelength of sound waves is comparable with the size of obstacles, whereas for light, the wavelength is much smaller than the dimensions of the most of the obstacles. Question number 20. Is the width of all secondary maxima in diffraction at slit is same? Question mark. If not, how does it vary? Again question mark. Answer. No. The width of secondary maxima in diffraction is not the same, as the order of secondary maxima increases its width decreases. Question number 21. What about the consistency of principle of conservation of energy in interference and diffraction? Please read the question once again. What about the consistency of the principle of conservation of energy in interference and diffraction? Or the question can be asked in another way. Or does the law of conservation of energy holds good in interference and in diffraction? Answer. Interference and diffraction are consistent with the principle of conservation of energy. 2 marks questions, short answers type 1. Question number 1. State Huygens principle. Answer. Each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. These wavelets emanating from the wavefront are called as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of wavefront at a later time. This principle is explained in our video number 10a. Please click the link given in the description part of the video. Question number 2. Name the wavefront obtained when a plane wave is passed through. Number 1. A thin convex lens. Number 2. Thin prism. Answer. Number 1. Spherical converging wavefront. Part 2. Plane wavefront. Question number 3. What is the shape of wavefront in each of the following cases? A. Light emerging out of a convex lens when a point source is placed at its focus. Part B. The portion of wavefront of light from a distant star intercepted by the Earth. Answer. A. Plane wavefront. Part B. Answer is plane wavefront. So, in both the cases, it is a plane wavefront. Question number 4. What are coherent sources? Give one example. Answer. The two sources are said to be coherent if the phase difference between the waves emitted by them at any point will not change with time. That is, the phase difference should not change, or any two sources continuously emitting waves having zero or constant phase difference are called coherent sources. That means if the phase difference is constant or phase difference is zero, then they are coherent sources. Example. In Young's double slit experiment, the two slits behave like coherent sources. Question number 5. Can two sodium vapor lamps be considered as coherent sources? Why? Answer. No. Because the phase difference between light coming from two independent sources continuously change. Question number 6. Write the expression for fringe width in Young's double slit experiment. Answer. The fringe width where beta is equal to lambda d by lambda capital D by small d, where lambda is the wavelength of the light, small d is the distance between the slits, and capital D is the distance between the screen and the slits. Question number 7. What are the factors which affect the fringe width in Young's double slit experiment? Answer. The wavelength of the light. The factors are the wavelength, the distance between the slits and the screen, or the slit separation. Any two will be the factors. Question number 8. Let the fringe width in Young's double slit experiment be beta. What is the fringe width if the distance between the slits and the screen is doubled and slit separation is halved? Answer. Initial fringe width is given by the formula beta is equal to lambda capital D by small d, and the new fringe, and when the distance between the slits and the screen is doubled and slit separation is halved, the new fringe width beta dash will be equal to lambda into 2 into capital D divided by small d by 2, and substituting and simplifying we get that is equal to 4 into lambda into capital D divided by small d. But lambda into capital D by small d is nothing but beta. Therefore, it becomes 4 beta. Therefore, the new fringe width becomes 4 times the initial fringe width. Question number 9. What is the diffraction of light? Give an example. Answer. The phenomenon of bending of light waves around the edges or corners of the obstacles and entering into the expected geometrical shadow of the obstacle is called diffraction of light. That is, phenomena is bending of lights around the edges is the diffraction, and entering into the expected geometrical shadow of obstacle is called diffraction of light. Example. Colors observed when CD is viewed due to the diffraction of light. Question number 10. Mention the conditions of diffraction, minima and maxima. Condition of secondary maxima is angle of diffraction theta is equal to within brackets n plus half into lambda by a, where n is equal to an integer. N is an integer plus or minus 1, plus or minus 2, plus or minus 3, etc. etc. Condition for diffraction minima is angle of diffraction theta is equal to n lambda by a, where n is equal to e plus or minus 1, plus or minus 2 and plus or minus 3, where lambda is the wavelength of light used and a is the slit width. Give the graphical representation to show the variation of intensity of light in single slit diffraction. Answer. So the graph on the screen is the variation of intensity with respect to distance from the center. Intensity is on the y-axis. See, this is intensity and this is the distance from the center. This is the graphical representation. Question number 12. In a Young's double slit experiment, the angular width of fringe formed on the distance is 0.10. The wavelength of light used is 6000 degrees Armstrongs. What is the spacing between the slits? So here given is width of the fringe 0.1 in degrees. Then the wavelength of light is 6000 Armstrong. What is the spacing? So let us solve it. Given theta is equal to 0.1 degree, that should be converted into 0.1 into pi by 180, that is equal to 1.745 into 10 to the power of minus 3 radians. And wavelength lambda is given by 6000 Armstrongs, that is equal to 6 into 10 to the power of minus 7. Now, the spacing between the slits is given by the relationship or formula small d is equal to lambda by theta. That is equal to lambda is 6 into 10 to the power of minus 7 and theta is equal to 1.745 into 10 to the power of minus 3. That is in the denominator. Simplifying, we get 3.438 into 10 to the power of minus 4 meters. 3 marks questions, that is short answers type 2. Question number 1. Using Huygens wave theory of light, show that the angle of incidence is equal to angle of reflection in case of reflection of a plane wave by plane surface. Answer. Consider a plane wave AB incident at an angle I on the reflecting surface Mn. If V represents the speed of wave in the vacuum and if tau represents the time taken by the wavefront to advance from point B to point C, the distance Vc equals V tau. In order to construct the reflected wavefront, a sphere of radius equal to V tau is drawn from point A as shown in the adjacent figures. Let CE represent the tangent plane drawn from the point C to this sphere. Equals V tau. There and angle ABC equals angle CEA, that is angle CEA equals 90 degrees and AC is common to both the triangles. Therefore, the triangles EAC and BAC are congruent. That is, angle I is equal to angle R. Hence, it is proved that the angle of incidence is equal to angle of reflection in case of a reflection of a plane wave by a plane surface using Huygens wave theory of light. Next question. Illustrate with the help of suitable diagram action of the following when a plane wavefront is incident. That is in case of a prism, number 2 a convex lens, and number 3 a concave mirror. Answer. Action of prism when a plane wavefront is incident on it. See, the incident plane wave is incident on a prism. This blue colored is a prism and the wavefront is outside it is a inclined one. In the figure A, consider a plane wave passing through a thin prism. Since the speed of light waves is less than glass, the lower portion of incoming wavefront, which is incident, which travels through the greatest thickness. See, this lower wavefront travels a longer distance in the prism and this travels in a lesser space. So, hence this reaches fast and it is inclined. And it gets, the lower part gets delayed, resulting in a tilt in the emerging wavefront. Number 2, that is the case of a convex lens. Please see the figure B with a convex lens. The blue colored is a convex lens and this is incident wave on the left hand side. In figure B, a plane wave is incident on the, this is a plane wave incident on the thin convex lens. The central part is thick. The central part of the incident wave traverses the thickest portion of the lens and is delayed most. The emerging wavefront has depression at the center and therefore the wavefront becomes spherical. Therefore, a sphere of radius equal to f the focal length and converges to a point of focus f. This is the convergent. Number 3. Action of concave mirror when a plane front is incident on it. In the figure C, this is the figure C, a plane wave is incident on the concave mirror and on reflection we have a spherical wavefront converging to F. This is converging. This is converging to the point F. Focus F. Next question. Briefly describe Young's experiment with the help of a schematic diagram. Answer. The diagram is as shown in the figure. S represents a pinhole. Here, the S represents a pinhole illuminated by sunlight. This is the sun ray falling on the pinhole. The spherical wavefront from S is incident on two pinholes S1 and S2, which are very close to each other and equidistant from S. So these both S1 and S2 are equidistant from S. Then the pinholes S1 and S2 act as two coherent sources of light of same intensity. Since the source is same, source S is same for both the slits S1 and S2, they act as coherent sources of light of same intensity. The two sets of spherical wavefronts coming out of S1 and S2 interfere with each other in such a way as to produce a symmetrical pattern of varying intensity on the screen placed at a suitable distance d. This is a screen. OP is a screen at a distance d from the slits S1 and S2. And the wavefronts coming out of S1 and S2 interfere with each other in such a way as to produce a symmetrical pattern of varying intensity on the screen. Question number 4. Distinguish between interference of light and diffraction of light. So column A shows interference. Is column A, the second column is for interference and this column is for diffraction. Serial number 1. Interference fringes have equal width. So the fringes of interference have equal width. Whereas in the case of diffraction, bands have unequal width. Width of secondary maxima decreases with increase in order. Number 2. Interference is due to superposition of two waves originating from two coherent sources. Diffraction is due to the superposition of secondary wavelets originating from different parts of a single slit. Serial number 3. Intensity of all bright fringes is equal and intensity of dark fringes is 0. So in the case of interference, there are bright fringes as well as dark fringes. In case of diffraction, intensity of central maximum is highest and the intensity of secondary maxima decreases with increase in order. Serial number 4. At an angle equal to lambda by A, maximum intensity for two narrow slits separated by a distance A is found. That is maximum intensity for at an angle lambda by A and at a distance A is found. Whereas in case of diffraction at an angle of lambda by a, the first minimum of diffraction pattern occurs for a single slit of width a. Serial number 5. In an interference pattern, there is a good contrast between dark and bright fringes. So, there is a very clear distinction between a dark and bright fringes. In a diffraction pattern, the contrast between the bright band and dark band is comparatively lesser. 5 marks questions, that is long answers type of questions. Using Huygens wave theory of light, derive Snell's law of refraction. This is pertaining to Snell's law of refraction. Let xy be a separating rarer medium 1 and a denser medium 2. The velocity of medium 1 is v1 and its refractive index is n1. The velocity of denser medium is v2 and its refractive index is n2. We know from the triangle ABC, BC is equal to v1 into t, where v1 is the velocity into time is the distance BC. Similarly, from triangle ADC, AD is equal to AD. This AD is equal to V2T. That is once again the distance is equal to velocity into time. From triangle ABC, we know sine of I, this is the angle I, angle of incidence, I is equal to BC by AC, where BC is the opposite side and AC is the hypotenuse. But BC is equal to V1T divided by AC. That is equal to sine of I. Let it be equation 1. Again, from the triangle ADC, AD, that is, this is the sine of angle, refracted angle. Sine of R is equal to opposite side AD by hypotenuse AC. That is AD is equal to V2 times T. That is V2 is the velocity of light in denser medium into T divided by AC. Let it be equation 2. Therefore, dividing equation 1 by equation 2, we get sine I by sine R is equal to V1 by V2. Let it be equation 3. But we know the velocity of light in medium 1 to the velocity of light in medium 2. That is, the ratio of V1 to V2 is equal to N2 by N1. That is the ratio of the respective refractive indices. Therefore, sin I by sin R is equal to sin I by sin R is equal to N1 sin, that becomes N1 sin I equals N2 sin R. This is Snell's law of refraction. Question number 2. Derive the expressions for resultant displacement and amplitude when two waves having the same amplitude and same phase difference superpose. Hence, give the conditions for constructive and destructive interference. Or the question can also be asked like, give the theory of interference, hence arrive at the conditions for constructive and destructive interferences. This is a 5-mark question. Answer. When two similar waves propagate in the medium simultaneously, then at any point the resultant displacement is equal to the vector sum of displacement produced by individual waves. Hence, the resultant of the combination given by y is equal to y1 due to wave 1 plus vector y2, which is a wave due to equation due to wave 2. That can be written as, because it is a sine wave, y is equal to, within big bracket, a of sine omega t, a of cos omega t plus a of cos omega t plus phi. Please note here phi, where phi is the phase difference. That can be written as, trigonometrically written as 2a cos of phi by 2 into cos of omega t plus phi by 2. Therefore, that is because we know cos of c plus cos of t is equal to, in terms of half angles, can be written as 2 of cos of c plus d by 2 into cos of c minus d by 2. This is from our knowledge of trigonometry. Hence, 2a cos of phi by 2 and cos of omega t plus phi by 2 can be written as, in this equation, this is a cos function, cos of omega t plus phi by 2, and 2a cos phi by 2 will be the amplitude of the resultant displacement. We know intensity is proportional to the square of the amplitude of the wave. Therefore, I is proportional to a square, or I is proportional to 2 E naught cos phi by 2 whole square. That is, I is proportional to E naught, or I can be written as equal to 4 times I naught into cos square phi by 2. That is simply squaring this. Therefore, condition for constructive interference. The interference taking place at points of maximum intensity. Please note, at points of maximum intensity is called constructive. When I is equal to I naught maximum, or 4 times I naught, for the constructive interference, I should be maximum. That is, cos of phi should be equal to 1, or when phi is equal to 0 or 2 pi or n pi, cos phi is equal to 1. So we know from our trigonometry, cos 0 is 1. Cos of 360 is 1. Or cos of n into pi is 1. So our path difference is given by delta is equal to n times lambda. Therefore, I max is equal to 4 times I naught, and the resultant amplitude is equal to 2a. Destructive interference. The interference taking place at points of minimum intensity is called destructive interference. For destructive interference, I should be minimum, or cos phi is equal to minus 1, or cos phi equals 0. Therefore, I is equal to I minimum is equal to 0. When phi is equal to pi or 3 pi or 5 pi or 2n plus 1 pi, phi is equal to 2m plus 1 pi, where n is equal to 0, 1, 2, 3. or path difference is delta is equal to n plus half into lambda. This is destructive interference takes place leading to zero amplitude and zero intensity.
Young's double slit experiment is used to find out the path length, the position of rings, dark and bright spots, and fringe width. So let us see the experiment setup. S is the source of light, and the beam of light passes through a single slit first, and then it passes through a double slit S2, and finally it converges at screen. So the distance between screen and the slits, two slits, is capital D, and the spacing between S1 and S2 is small d, and we are required to determine y, the distance between O and P. Here O is the center of the screen. The wave from S1 and S2 reach the point P with some phase difference, and hence path difference delta is equal to S2P minus S1P. So this is S1P and this is S2P. The difference of S2P and S1P, that is the path length, is delta. So we have to study the geometry of the diagram shown here. To find an equation for the path difference and position of fringes, we know that we have given delta is equal to S2P minus S1P. This is S1P and this is S2P. Therefore, we will consider separate squaring S2P square minus S1P square. So using algebra knowledge, here S2P is d square, that is S2P is hypotenuse d square plus y plus d by 2 whole square, minus S1P is d square once again plus y minus d by 2 whole square. Therefore, this S2P p square minus S1P square can be expanded as S2P minus S1P into S2P plus S1P, that is A plus B, A square minus B square is equal to A plus B into A minus B. See, this simplifying we get 2D. Therefore, delta into 2D, S2P minus S1P is delta, and S2P plus S1P can be regarded as 2D because D is far larger than small d, and it will be, they will be almost, if D is very large, S1P and S2P will be equal. That will be 2D. That is equal to 2D on the right hand side. Therefore, path length delta will be is equal to yd by d. So here we can write it is a multiple of n into lambda. That can be written as position of y fringes will be is equal to y equals d into n lambda divided by small d. That is the position of y fringes. So path difference delta is equal to yd by d. Coming back to this main equation, delta is equal to yd by y small d by capital D, 10.7a. In condition for constructive interference resulting in bright fringes, the path difference is equal to, we know, n times lambda, where n is the number of fringe, is an integer, and lambda is the wavelength. Therefore, y into small d by capital D is equal to n into lambda. That this is the n into lambda is the condition for constructive interference. Therefore, y equals n into lambda into capital D by small d. Let the equation be 10.7. 10.7c. So the distance between two consecutive bright rings is called fringe width. Therefore, if y is the y1, yn is the fringe is the distance distance of first ring, and yn plus 1 is the second ring, the position of second ring, the distance spacing between the two is called the fringe width. Therefore, beta is equal to y into y suffix n plus 1 minus yn, that is equal to lambda d by t. That is the difference. Fringe width is given by lambda capital D by small d. Therefore, a bright fringe is at theta equal to 0, that is on the central axis. This is the central axis. Here theta equal to 0. This theta, this angle of separation is 0. Yeah, that's why we get a bright path. And hence here the phase difference is 0 and path length is also 0. That is why we get a bright spot here. Now we will take up destructive interference. Condition for destructive interference resulting in dark rings. That is, the destructive interference results in dark rings and constructive interference results in bright rings. Therefore, path difference here will be n plus half into lambda, that is half multiple of wavelength. Here full multiples, integer, that is n is a full integer 0, 1, 2, 3, and here 0 plus half, 1 plus half, so n plus half of lambda. So path difference will be n plus half into lambda, therefore 10.7 e. Substituting this in this equation, we get y into small d by capital D is equal to n plus half into lambda, or y is equal to 2 within brackets 2n plus 1 into lambda d by 2d. This is the path difference for destructive interference. Let it be equation 10.7 f. Dark and bright rings are equally spaced, and the distance between the two dark rings is also called the fringe width. So fringe width is the distance either the distance between two bright rings or two dark rings. These are represented by beta equals yn plus 1 minus yn, which can be either for two consecutive bright rings or for dark rings.
Next question. Explain the phenomenon of diffraction of light due to a single slit and mention the conditions for diffraction, minima and maxima. This is a 5 marks question in your examination. Answer. Diffraction of light at single slit. When a single narrow slit illuminated by a monochromatic light source, a broad pattern with a central bright region is seen. On both sides, there are alternate dark and bright regions. The intensity becomes weaker away from the center. A parallel beam of light falling normally on the single slit. This is the single slit, and these are the blue colored arrows are beam of light, parallel beam of light. It falls on a single slit Ln. L is at the top, Ln. This is a single slit Ln. The width of the slit is A. The diffracted light goes on to meet on the screen. This is a screen which is away from the slit, and because of shortage of space, this space is cut and shown as this screen. And all these rays either converge onto the point P. The diffracted light goes on to meet on the screen. The midpoint of the slit is M. You see, here it is M. A straight line through M perpendicular to the slit plane meets at the screen at C. This line meets here. So there is little bit difference here and there, but it is this C, this light midpoint meets at the center at C. The straight lines joining P to the different points of L, M, N, etc. can be treated as parallel. So the meeting these points can be treated as parallel, making an angle theta. Here it is an angle theta with normal MC. This is to divide the slit into smaller parts and add their contributions at P with proper phase differences. Different parts of wavefront at slit are treated as secondary sources. The different parts of the slit are treated as secondary sources. Because of the incoming wavefront is parallel to the plane of slit, these sources are in phase. The path difference between the two edges of the slit N and P is NP minus NQ. This is LP and NP. This is NP and this is LP. See, the path difference is NQ shown here. That is equal to A sin theta. That is A is this one horizontal. This one A sin theta. Theta is the angle. This is A sin theta. The slit is A and theta is the angle A sin theta. NQ is equal to A sin theta, that is equal to A theta. Therefore, at the central point C on the screen, this is the point C on the screen, the angle theta is 0. Here, if you see, the angle theta is 0. The path difference is also 0. And hence, all the parts of the slit contribute in phase. This gives a maximum intensity at C, that is central maximum. This is central maximum. Secondary maxima is formed at theta is approximately equal to n plus half into lambda by A, where n is an integer plus or minus 1, plus or minus 2 or plus or minus 3. That means the secondary maxima is also formed on the either side of the central bright. Minima that is at dark, zero intensity is formed at theta is approximately equal to n lambda by A, where n equals plus or minus 1, plus or minus 2 or plus or minus 3. The relationship is also shown in the tabular column. The angle theta is 0, that is central maxima. At central maxima, theta equals 0 and the brightest of all points, brightest at central maxima. And when theta is equal to n lambda by A, that is minima occurs, a dark, that is A theta equals lambda and it is a dark spot, wherein the slit is divided into two parts, 0 to 6 and 6 to 12. And in the third case, when the angle is 2n plus 1 into lambda by 2a, or as written here, n plus half into lambda by a, the path difference is 2n plus 1 into lambda by 2. Therefore, the secondary maxima occurs here and the secondary bright spots. This is also shown in the graphical representation. Central maxima occurs here at the central point. This is the brightest spot and secondary maxima is here, this on the either side, and minima is at this point, the 0, where the distance from the center, that is the distance from the center, and the amplitude is 0 here. This is 0, this is 0. It goes maximum and comes down like this. For answering this question, you need not write this graph or a tabular form. These are given here to explain it very clearly. Five marks question. Here in this section, we will solve numerical problems of 5 marks each. Question number 1. A monochromatic yellow light of wavelength 589 nanometer is incident from air on water surface. What are the wavelength, frequency and speed of refracted light? Refractive index of water is 1.33. This is a simple problem on refraction of light. When light travels from air to water, we are required to calculate wavelength, frequency and speed of a refracted wave. Answer given lambda is equal to 589 nanometers, that we have converted as meter, 5.89 into 10 to the power of minus 7 meters. And it is also given refractive index of water is 1.33. Therefore, for refracted light, the wavelength is given by the lambda dash is equal to lambda by n, where lambda is the wavelength in air divided by the refractive index. Given 5.89 into 10 to the power of minus 7 divided by 1.33. Therefore, simplifying, we get the answer as 4.43 into 10 to the power of 7. Frequency does not change when the ray of light travels from air to water. The frequency is unchanged. So frequency is same. Speed of refracted light. It is given by the new speed is given by v dash is equal to v into that is equal to c by n. That is where c is the velocity of the light in vacuum or air, that is equal to 3 into 10 to the power of 8 divided by 1.33. Simplifying, we get the value as 2.25 into 10 to the power of 8 meters per second. Question number 2. In a double slit experiment, angular width of a fringe is found to be 0.2 degrees on a screen placed 80 centimeters away. The wavelength of light used is 600 nanometer. Find the fringe width. So, the angular fringe width is given as 0.2 degrees. And the wavelength is also given as 600 nanometers. We have to find the fringe width in part 1. And next part, what will be the angular width of fringe if the entire experimental apparatus is immersed in water? Take the refractive index of water to be 4 by 3. So, first we have to find out the fringe width in case A, that is upper part, and the next, when the apparatus is immersed in water, what will be the fringe? Answer. Given angular fringe width is 0.2 degrees. This has to be converted into radians. Therefore, for converting 0.2 degrees into radians, we have to multiply it by pi and divide by 180 degrees. That becomes 3.49 into 10 to the power of minus 3 radians. Therefore, the fringe width beta is 3.49 into 10 to the power of minus 3 into 0.8. That is equal to 2.79 millimeter. When the entire experiment apparatus is immersed in water, wavelength of light lambda dash is equal to lambda by n, where Lambda dash is the wavelength in water and lambda is in air and n is the refractive index. Therefore, we have to divide the value. Lambda we know it is, in the first case it is 0.2 degrees, that is 3.49 into 10 to the power of minus 3. That should be divided by n. N is given as 4 by 3. Therefore, 4 by 3, it becomes 0.15 degrees. This is the answer. Next question. A ray of light consisting of two wavelengths 650 nanometers and 520 nanometers is used to obtain interference fringes in Young's double slit experiment with capital D is equal to 60 centimeters and small d is equal to 1 millimeter. Question A. Find the distance of the third bright fringe on the screen from central maximum for a wavelength of 650 nanometers. Part B. What is the least distance from central maximum where the bright fringes due to both the wavelengths coincide? So we have to understand the concept. First, it is two wavelengths. It is having 650 nanometer and 520 nanometer, and we are required to find the interference fringes in Young's double slit experiment. So it is connected with interference. D, where capital D is given, small d is given. So we are required to find the distance y on the screen from central maximum and also the distance y from central maximum where the bright fringes due to both the wavelengths coincide. Answer. So let us note down all the given parameters. Given lambda 1 is equal to 650 nanometer, that has to be converted into meter. That becomes 650 into 10 to the power of minus 9 meters. And lambda 2 is given as 520 into 10 to the power of minus 9 meters. Part A. The distance of nth bright fringe on screen from central maximum is given by yn is equal to n into capital D lambda by small d. Therefore, y3 is equal to, because nth for the question asked is for the third bright fringe. So y3 is equal to 3 into, that is n, value of n as 3 into 0.6 into 650 into 10 to the power of minus 9 divided by 1 into 10 to the power of minus 3. This is by simply substituting the values of n, capital D, lambda and d. We get the answer as 1.17 millimeter. Part B. For least distance y, the nth bright fringe due to longer wavelength lambda 1 coincides with the n plus 1 bright fringe due to shorter wavelength, wave of shorter wavelength. So this is given by the formula n into d into lambda 1 divided by small d, that is equal to n plus 1 into d into lambda 2 divided by d, or cancelling the common factor, d and d gets cancelled, capital D and capital D also gets cancelled. Therefore, n into lambda 1 is equal to n plus 1 into lambda 2. So, the distance is given by the formula, distance of The fourth, nth bright fringe due to longer wavelength is given by y4 is equal to 4 into capital D into lambda 1 by small d. So substituting the values, 4 into capital D is 0.6 and lambda 1 is 650 into 10 to the power of minus 9 divided by small d 1 into 10 to the power of minus 3. Simplifying, we get the answer as 1.56 into 10 to the power of minus 3 meters. In this problem, you have to remember this nd lambda 1 by small d is equal to n plus 1 into capital D lambda 2 by d. This is important. This is the condition for least distance y and the nth bright fringe due to longer wavelengths. Question number 4. In Young's double slit experiment, using monochromatic light of wavelength lambda, the intensity of light at a point on the screen where path difference is lambda is k units. That means the intensity of light is given as k units when the path difference is lambda. The question asked is, what is the intensity of light at a point when the path difference is condition 1 lambda by 3 and second question is lambda by 2. Therefore, for lambda, the intensity is k. What is the intensity for lambda by 3 and lambda by 2? So let us understand that it is due to interference. This problem is for interference. So given I is equal to k when the path difference is lambda. This is given. Both are given. So we are required to find lambda by 3 path difference at lambda by intensity for path difference at lambda by 3 and lambda by 2. If the phase difference between two waves is phi, then the intensity at that point is I is equal to I naught into cos square phi by 2. This is the formula. We have to identify this formula for this problem because it is associated with intensities. So it is given phi is equal to path difference is equal to lambda when the phase difference is phi is equal to 2 pi. That is, if the path difference is lambda, phase difference is 2 pi. This you have to remember. Therefore, substituting in this formula, that is I is equal to I naught into cos square by phi by 2, where phi is equal to 2 pi, we get I is equal to 4 times I naught cos square into 2 pi by 2. This is the formula that is equal to 4 times I naught, that is equal to given as k, that it is given. Therefore, for the first part we have to substitute phi as 2 pi by 3, that is for lambda 2 pi. So for lambda by 3 it is 2 pi by 3. Therefore, phase difference phi is equal to 2 pi by 3. Lambda by 3 here and 2 pi by 3. Therefore, the intensity at that point is given by the formula I is equal to 4 times I naught cos square into 2 into 2 pi by 3 divided by 2. Therefore, that is here this 2 and this 2 gets cancelled and this 2 and this 2. This 2 is for square, cos square. So this 2 and this 2 and the pi by 3 remains. Therefore, 4 I naught cos squared into pi by 3. Therefore, but for I naught, we know 4 I naught is k. Here you see 4 I naught is k. It is given. Therefore, k into cos of pi by 3. That is pi by 3 is 60 degrees. 60 degrees. Cos 60 is 1 by 2. And cos square is, this square is retained. Therefore, the value is k by 4. This is the answer. So, for second part, we have to substitute the value of part difference as lambda by 2 or phase difference as phi is equal to pi. So, you see here, when it is lambda, part difference is lambda, it is 2 pi. When it is lambda by 2, it should be phi is equal to pi. So, it is phi is equal to pi. Therefore, intensity at that point is I is equal to 4 times I naught cos square pi by 2. So, pi by 2 is cos 90. Cos 90 is 0. Therefore, it becomes 0 into 4 I naught. The answer is 0. A beam of light of wavelength 500 nanometers falls on a narrow slit and resulting a parallel beam of light of wavelength 500 nanometer falls on a narrow slit and the resulting diffraction pattern is observed on the screen 1.25 meters away. It is observed that the first minimum is at a distance of 2.5 millimeter from the center of the screen. Find 1. The width of the slit. Number 2. Angular position of the first secondary maximum. So this problem is pertaining to diffraction, where a parallel beam of light is of wavelength 500 nanometer falls on a narrow slit. Let us solve it. Given I is equal to 500 nanometer, that is equal to 5 into 10 to the power of minus 7 meters, that is lambda. Lambda is equal to 500 nanometers. And capital D is given as 1.25 meter. You see here it is given 1.25 meter. And the value of y, that is the distance, is given as 2.5 meters. That is 2.5 meter from the central maximum. That is equal to, converting this 2.5 millimeter into meters, it becomes 2.5 into 10 to the power of minus 3. Angular position of first minimum. We have to remember the formula. Tan theta is equal to theta equals y by d. Y we know it is a distance on the screen, and capital D is the separation between the slit and the screen. Therefore, both the values are given. We get the value of theta as 2 into 10 to the power of minus 3 radians. So the first question asked it, we are required to find out the width of the slit. The width of the slit we know A is given by A is equal to lambda by T. Lambda by theta, that is equal to 5 into 10 to the power of minus 7. It is given lambda, and theta is 2 into 10 to the power of minus 3. That is equal to 2.5. Simplifying, we get 2.5 into 10 to the power of minus 4. So width of screen is 2.5 into 10 to the power of minus 4 meters. Part 2. Secondary maxima is formed at, we know from the formula, we have to remember theta is equal to, theta approximately equal to n plus half into lambda by A. This is the formula for secondary maxima. For the first secondary maxima, n is equal to 1. So, the question asked is angular position for the first secondary maxima. Therefore, we have to substitute the value of n as 1 because the question asked is first secondary maxima. Thus, the angular position of first secondary maximum is given by substituting this formula. Theta is equal to 1 plus half, 1 and a half, that is equal to 3 by 2. 3 by 2 into lambda by a. Therefore, retaining 3 by 2 into 5 into 10 to the power of minus 7 divided by 2.55 into 10 to the power of minus 4. Simplifying, we get the values as 3 into 10 to the power of minus 3 radians. Question number 6. In a Young's double slit experiment, the slits are separated by 0.28 millimeter. The screen is placed at 1.4 meters. The distance between central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. Determine the wavelength of light used in the experiment. Also find the distance of fifth dark fringe from the central bright fringe. So therefore, we have to calculate two things. One is wavelength and second is distance of fifth dark fringe. Other parameters are given and we have to recollect the formulae applicable in this problem. Let us do it. Answer. Given D is equal to the distance between slit and screen as 1.4 meter. It is given. Screen is placed at 1.4 meter. And separation is given as the fourth separation as, you see here, fourth bright fringe. So therefore Y4 is equal to 1.2. So here we have to substitute the value of n as 4. That is equal to the 1.2 centimeter should be converted into meter. That is 1.2 into 10 to the power of minus 2 meter. Small d, that is the separation between two slits, is given as 0.28 millimeter. You see here the slits are separated by 0.28 millimeter. That also we have to convert into meters. That is 0.28 milli means 10 to the power of minus 3 to 0.28 into 10 to the power of minus 3 meters. So we are required to find out the wavelength lambda. And for the fifth dark fringe, the separation y. So two things, one lambda and the second is separation, distance between the central and the fifth dark fringe. So let us solve it. The formula applicable is yn is equal to n into d lambda by capital D by small d. Therefore, wavelength lambda we can rearrange and calculate. That is, lambda is equal to yn into d divided by n into d. So, putting the value of yn, y suffix n as 1.2 into 10 to the power of minus 2m into capital D is 0.28. That is a small d here. Small d is equal to 0.28 into 10 to the power of minus 3 divided by n. N is equal to 4 here in this case. Okay, 4 into 1.4. 1.4 is the value of capital D. Therefore, simplifying, we get wavelength lambda as 600 nanometers. Distance of the dark fringe from central bright fringe is given by the relationship. You have to remember y is equal to n within brackets n plus half close the bracket into capital D into lambda by small d. Here n is equal to 4 for fifth dark fringe. This you please remember, for fifth dark fringes, n is 1 less than the actual number of dark fringe. Therefore, y is equal to 4 plus half into 1.4 into 6 into 10 to the power of minus 7 divided by 0.28 into 10 to the power of minus 3. Simplifying, we get the answer as 1.35 centimeter. Next question. In Young's double slit experiment with monochromatic light, slit separation of 1 mm, that is small d is equal to 1 mm, the fringes are obtained on screen placed at some distance from the slits. If the screen is moved by 5 centimeters towards the slit, the change in fringe width is 30 micrometer. Calculate the wavelength of the light. Here, please understand the concepts. It is a double slit experiment. The distance capital D is reduced by 5 centimeter. You see, the screen is moved 5 centimeters to a slit. And he also says the fringe width is changed by 30 micrometer. So he has given change in capital D and change in beta, that is the fringe width. And we are required to calculate the wavelength of the light. Let us do it. Given small d is equal to 1 mm. You see here the slit distance between two slits is 1 mm, that is equal to 10 to the power of minus 3 meter. Let the initial distance of the screen of slits be d. Therefore, when the screen is moved 5 centimeter, the new distance will be equal to d dash is equal to d minus 5 into 10 to the power of minus 2. That is 5 centimeter. This is 5 centimeter or minus 5 into 10 to the power of minus 2 meters. Therefore, the corresponding reduction in fringe width is b dash is equal to b minus 30 micrometer. Micrometer means 10 to the power of minus 6 meters. So therefore, beta dash is equal to beta minus 30 into 10 to the power of minus 6 meters. So the initial fringe width we know beta. Here beta is equal to lambda d by small d, capital D by small d. This formula you have to remember. Therefore, beta dash will be equal to beta dash for after changing the distance, reducing the distance from capital D to D minus 5 of 10 to the power of minus 2. So, B dash is equal to lambda into D minus 5 into 10 to the power of minus 2 divided by small d. Therefore, beta, we know the new beta is beta minus 30 into 10 to the power of minus 6. Beta dash value of beta dash is this. And lambda into d, simplifying d divided by d. This lambda into this capital D and small d. So this item is written here. Minus lambda into 5 into 10 to the power of minus 2 divided by d. Therefore, simplifying, so this lambda d by small d is beta. So we will put that value as beta. So left part, beta minus 30 into 10 to the power minus 6, we will retain as it is. This as beta minus lambda we will write as it is. Lambda we are required to find out divided by small d. Small d is 1 millimeter, 10 into 10 to the power of minus 3 into 5 into 10 to the power of minus 2. Therefore, that becomes lambda is equal to 30 into 10 to the power of minus 6 into 10 to the power of minus 3 divided by 5 into 10 to the power of minus 3. That is equal to 6 into 10 to the power of minus 7. That is, the value is 600 nanometer. With this, we come to the end of this 5 marks numerical problems. Multiple choice questions. In a Young's double slit experiment, the separation between slits is 0.1 mm. The wavelength of light used is 600 nanometers, and the interference pattern is observed on a screen which is kept 1 meter away. Find the separation between bright fringes. Options: A 6.6 mm, option B 6 mm, option C 6 meters, and D 60 centimeters. We had to use the formula beta is equal to lambda capital D by small d, where small d is 0.1 mm and lambda is 600 nanometers, 600 nanometers, and capital D is 1 meter away. The correct answer is B. Question number 2. In Young's double slit experiment, the distance between two consecutive bright and dark fringes are given by. We have to identify the formula. Option A, beta is equal to lambda capital D by D. Option B, beta is equal to capital D into small d by lambda. And option C, beta is equal to lambda divided by capital D into small d. And option D is beta is equal to lambda d by capital D. The correct answer is A. Question number 3. In the Young's double slit experiment, the fringe pattern as seen on the screen is A. Parabola, B. Hyperbola, C. Ellipse, option D. Spiral. The correct answer is B, that is hyperbola. Question number 4. The light source used in Young's double slit experiment are incoherent, option A, option B coherent, option C white light, option D blue, green and red light. Correct answer is B. You have to remember it. Question number 5. What is the effect of angular width of interference fringes in a Young's double slit experiment when screen is moved nearer to the plane of the slits? 4 options are increases, option A, option B decreases, option C constant, and option D not defined. Correct answer is C. Question number 6. The phase difference between two waves at the place of constructive interference is given as a multiple of A. Multiple of pi, B. Multiple of 2n minus 1 into pi, and option C. Even multiple of pi, option D. Odd multiple of pi. Correct answer is C, that is even multiple of pi for constructive interference. Please note constructive interference. Question number 7. The path difference between two waves at the place of destructive interference is given by multiple of lambda, a multiple of lambda by 2, even multiple of lambda by 2, option D is odd multiple of lambda by 2. The correct answer is D. Number 9. Question number 9. Bending of light phenomena is shown by polarization, diffraction, option C interference, and option D dispersion. The correct answer is B. That is, bending of light phenomena is shown by diffraction. Next question. Angular width of interference fringe depends on A. Distance between slit and screen, wavelength of light, the ratio of wavelength and slit width, and option D, width of the slit. Correct answer is B. Next question. Resolving power of telescope depends on, you can skip this question. Next question. In phenomena of diffraction of light, when the violet light is used in the experiment, I will read the question again. In the phenomena of diffraction, when violet light is used instead of red light, then option A, fringe width increases. B, no change in the fringe width. Option C, fringe width decreases. Option D, color pattern is formed. Option is C, that is, fringe decreases. Next question. Diffraction aspect is easier to notice in case of a sound waves than in the case of light waves because sound waves are A, have longer wavelength, B, shorter wavelength, C, longitudinal wave, and D is transverse. Answer is A. Sound waves have the longer wavelength. Next question. The wavefront due to source situated at infinity is spherical, B, plane, C, cylindrical, D, rectangular. We have to choose the correct answer. The correct answer is B, plane. Next question. Colors appear on the thin film of a soap and a soap bubble is due to A, diffraction, refraction, option B, refraction, option C, dispersion, option D, interference. The answer is D. Completion type questions. Number 1. In Young's double slit experiment, the fringe width is given by dash. Answer is beta is equal to d lambda by d. This you have to remember. The phase difference between two waves in dash interference is given as even multiple of pi. The answer is constructive interference. Question number 3. Fringe width is different as the separation between two consecutive dash or dash. It can be, the answer is maxima and minima or minima. Maxima or minima. Question number 4. Dash of light occurs when size of obstacle aperture is comparable of wavelength of light. Dash of light occurs when size of the obstacle of aperture is comparable with wavelength of light. Answer is diffraction of light occurs. Next question. During reflection or refraction of light, dash remains unchanged. Answer is frequency. Question number 7. Continuous locus of oscillation with constant phase is called as dash. Answer is wavefront. Question number 8. In interference and dash, the light energy is redistributed. That is, increases in one region and decreases in other. That is, in interference and diffraction, the light energy is redistributed. Next question. Intensity of light is determined by dash of the amplitude of oscillations. That is, intensity is determined the square of the amplitude. That is, I is proportional to A square. True or false type questions. Question number 1. Sustained interference is caused due to superposition of two waves coming from two coherent sources. Answer. True. Question number 2. Fringe width is defined as separation between two consecutive maxima or minima. True. Question number 3. When white light is used to illuminate the slit, we obtained an interference pattern consisting of a central white fringe having a few colored fringes on two sides and uniform illumination. True. Question number 4. Fringe width is given by beta is equal to d divided by capital D divided by small d into lambda, where d is the separation of coherent sources, capital D is the distance of screen from source, and lambda is the wavelength. Answer is false. The correct formula is beta is equal to lambda into capital D divided by small d. Question number 5. The phase difference between two waves at the place of constructive interference is given as an even multiple of pi. Answer. It is true. Question number 6. Light is a longitudinal wave. Answer. It is false. Question number 7. In a single slit experiment, the slit width is doubled. That is, the small d is doubled. Then the original width intensity increases 4 times the initial intensity. Answer is true. Question number 8. Bending of light phenomena from corners of obstacles or aperture is related with interference. It is false. Actually, bending of light is related to diffraction. Question number 9. Diffraction of light occurs when the size of aperture is comparable to the wavelength of the light. True. Question number 10. Diffraction is interference due to wavelength from different parts of the same wavefront. True. Question number 11. Intensity of light is maximum on either side of central maxima is same in case of diffraction. That is, he says intensity of light is maximum on either side of central. That is false, because at central only it is maxima. Question number 12. The path difference between two waves originating from two coherent sources for constructive interference at a point should be n, where n is equal to 0, 1, 2, 3, etc. Answer is true. Matching type questions. In this question, statement in column A should be matched with the correct statement in column B. Let us start. Question serial number 1. 1A. In YDSE, Young's double slit experiment, when width of one slit is slightly increased, then maximum intensity will increase. Option B. Question B. In YDSE, when one slit is closed, the correct answer is interference pattern will disappear. Question number 2a. In YDSE apparatus is immersed in a liquid, fringe width will decrease. Question 2b. When wavelength of light used is increased, the fringe width will increase. That is, B is 1. Correct answer. 3a. Single slit experiment is for diffraction, whereas 3b. Double slit experiment is for interference. B is 3. Question 4. 4a. Point source. Point source. The wavefront is spherical wavefront for a point source. Rectangle 4b. Rectangular slit kept in front of a distant source is 1. That is plane wavefront. Question 5. The first and 5 will be deleted. In this slide, we have given a number of formulae associated with wave optics. The main division is between interference of light and diffraction of light. There are about 9 formulae in interference of light and about 3 in diffraction. Please write down very clearly. These are very important formulae which will clearly explain different phenomena and different concepts of wave optics. Number 1. Interference of light. The resultant intensity I is given by I is equal to 4 I naught into cos square phi by 2, where phi is the initial phase difference between the waves and I naught is the intensity of both waves. Resultant intensity at a point in a region of superposition. So there are two waves with I1 intensity or A1 whose amplitude is A1. A1 and A2 are two amplitudes of waves 1 and 2 respectively. Therefore, I is given by A1 square plus A2 square plus 2A1 A2 into cos phi, where phi is the phase difference. It is also given by I1 plus I2 plus 2 into square root of I1 I2 cos phi. Please note the difference. Here it is in terms of amplitude. The second equation is in terms of intensity. Formula 3. The condition for maxima in interference. Phi should be 2n pi, where n is equal to 0, 1, 2, 3. And the path difference delta is equal to n lambda. Condition for minimum. The phase difference should be phi is equal to 2n minus 1 into pi. Please note the difference in phase between maxima, where it is 2n pi, and 2n minus pi for minimum. And delta is also 2n minus 1 into lambda by 2. Fringe width beta. Beta is equal to capital D into lambda divided by D, where capital D is the distance between slits and the screen and small d is the separation between slits, two slits, and lambda is the wavelength. The angular fringe width beta t, so beta suffix theta equals beta suffix theta is equal to beta by d, that is equal to lambda by d, where lambda is the wavelength of the light used and small d is the separation between the slits. Please clearly see the difference between beta by capital D and lambda by small d. This you please note and repeat the formulae. Number 7. Minimum amplitude A minimum is given by A minimum is equal to within brackets A1 minus A2. Serial number 8. Minimum intensity I minimum. Intensity I minimum is given by I minimum is equal to A1 minus A2 whole square, where A1 and A2 are the amplitudes of wave 1 and wave 2 respectively. Similarly, I minimum can also be written as I minimum is equal to I1 plus I2 minus 2 into square root of I1 I2. Number 9. Position of n maxima. N maxima is given by Yn. Yn equals n into capital D into lambda divided by small d. Similarly, for minima, Yn is given by Yn is equal to n minus half, close the bracket, within brackets, into d lambda by d. I will repeat the formula. Yn is equal to, within brackets, n minus half, close the bracket, d into lambda by d. Now these 9 or 10 formulae have been given for interference. Now diffraction. Here in diffraction, the first one is position of nth minima. Nth minima is given by d is equal to sine theta, that is equal to n lambda, where d is the width of slit and theta is the angle of diffraction and lambda is the wavelength and n is an integer. Number 2. Linear half width of central maxima. Linear half width, that is equal to y equals capital D into lambda by d. Lambda is the wavelength of the light years. Number 3. Total linear width of central maxima, that is given by B naught. Total linear width is given by B naught or 2y is equal to 2 into capital D into lambda divided by small d. Please repeat all these formulas. These are all very important, and if you practice it, you will clearly know the difference between various parameters, and your concepts and your remembrance of formula will be strengthened.